All right, y'all, I'm gonna go and get started now, just make sure that I have time to get through everything. But I want to continue with where we kind of left off yesterday with this idea that we're going into a new type of function. We didn't necessarily spend a lot of time with exponential functions because we've worked with exponents, right? The difference is, hey, when I have an exponential function, be familiar with the graph, the behavior of that, right? We're going to come back to exponential functions so here after we deal with logs, because now we're going to be able to deal with equations a little bit more. And we're going to start to see that today. But we have to establish some things with logarithms. Okay, as I said, this is a new operation. Many of you probably have never seen logarithms before, right? So we need to establish what are some rules here. Okay, remember I did the same thing with exponents. So kind of like what are some different exponents? Don't forget the product rule, don't forget the quotient rule. We need to do kind of the same pattern there. With that said, what do I do with this one here? Log of 2 times 5. What would someone do to start that problem? Order of operations, right? Multiply what's inside. So that's where we're going to get log of 10. What does the log of 10 equal though? What's missing with this logarithm right now? Well, we're not looking for, we're looking for the base, right? It doesn't show a base, right? So there's two things the base could be then. Either 10 or E. What is this one? It's base 10, right? So what is log base 10 of 10? Is 1, right? 10 to the first power gives us 10. Okay, so make sure you remember though, that definitely goes back to making sure you remember when it's not there, that means it's log base 10. That's what the common log is, okay? But make sure you see here, as I point out, that definitely don't forget the order of operations, okay? That comes with that. Questions? All right, what's going on with the next one? Log base 6 of 1,296. Not really a nice one, right? What's the number we're focused on now though? We have 1,296, but the only number we're really interested in right now is the base 6, right? So by hand, we could just start dividing out sixes, right? And we get what, 216? Divide out of 6, we get 36. Divide out of 6. We finally get a bunch of factors of 6 here, right? Specifically, how many factors did I show you? All right, you know, hey, we kind of knew to use the 6, so that helps a lot, right? But understand what this is asking us is what exponent would we want? Well, hey, that's going to be the 4. That's where the 4 comes in. Hey, I counted up to 6. 6 to the 4th is what equals the 1,296. Not something I would expect you to have off top of your head, but just remember when you get a problem like that, just start dividing by 6 and see how many times it works. Okay. It's not guaranteed to work all the time though. So keep in mind, as we looked at yesterday, where the best we do is give a decimal approximation. Okay. What about the next one, the natural log of E? What does that equal? What natural log of E equal? Goes back to remembering the base here, right? If this is the common log, this is the natural log. So this is base 10. So what's the base of the natural log? You don't write it, but it's base E. And when the base matches the argument, it's always going to be 1. Okay. I know this isn't everything that we did yesterday, but I felt it was like a good little highlight of some of the things to watch for. What's going on when the argument's 1? So like this last one though, I have log base 3 of 1. All right, so 3, so what exponent would give us 1? It goes back to our parent function, right? Hey, anything to 0 gives me 1. So it didn't matter that it was base 3. Could have been any base. This is going to equal 0. Okay. Now what you're going to find today was we need to expand upon that a little bit. And it's very important that we do. All right, these are great as far as just some quick ones, just making sure we get familiar with these things. Watch out for the log of 10. Watch out for the natural log of E. Know that with other bases, just try to see if it works out nicely. It's not guaranteed to do that again. I picked 1296 because it was 6 to the fourth power. Okay, so that's where that came from. Now, with that said, though, don't forget about using our inverse statement, right? So how could I rewrite y equals 2 to the x as an inverse? Not 2y, but log base 2 of y is the key. The 2's definitely needs to get paired with the y, though. That part we do need to see here, okay? But instead of an exponential, now we have a logarithm. What changes with the second one I put here? Start with a logarithm, right? So I need to change it to a exponential, right? Just make sure you see here, be careful to leave the x minus 4 by itself. And over here, 3, and then y plus 2 becomes the entire exponent. Okay. Now you're going to find the situation kind of determines what you need to do and how you handle it, right? That's one thing that we're going to look at is, situational, just kind of looking at and analyzing what we're working with and what we need to do. Okay. What we're going to find today, though, is that we need to expand upon some of these things that we work with now to make sure we have a good foundation for the logarithms. Okay, so we need to go through some properties. So is there any questions with these, though, before we look at some properties? All right, the good news is exponents and logarithms are closely related, so we're going to go through this one pair at a time. Okay, what does the product rule of exponents tell us to do, though, whenever we have, say, something like x to the m times x to the n? The exponents, right? Now, is that mean logarithms is going to be completely different? Not necessarily, right? We're just going to find that the way we write it's going to be different, okay? One thing that I want you to see here is we go from exponents, we're going to deal with the logarithms, right? The key here is it's a single logarithm, and where's the multiplication at that I'm showing? It's inside the parentheses, right? It is the argument of the logarithm. That's an important thing to see here. So I have a logarithm, the multiplication inside. I can use the product rule by saying, hey, I can take one logarithm and write it as two separate logarithms. That's what we're going to call the product property of logarithms, though, as we look at this. All right. I took the x and y and I separated to each of their own logarithms. What did I put in between them? Plus sign. So it's still addition, right? As we saw before, we add the exponents together here. The difference is, though, we're taking an inverse perspective. So it does look different, but there are similarities. So make sure you see that. What did I put on both of these logarithms, though? That's very important that we don't forget. The A, right? That base is very important. It's like up here having this, making sure it still matches the base that we had before, okay? What was the quotient rule? Subtraction, right? So the same kind of idea, but subtraction. Now, one thing I want to point out here with the quotient rule, remember that you could have wrote this as x to the m times x to the negative n, right? And then you would have m plus negative n as your exponent, which guess what? Addition of a negative is what subtraction is, right? So keep that in mind that if you ever get stuck, negative exponents is another way to handle something. Okay, if you get stuck, remember negative exponents can help. We got the negative exponents so from our exponential graphs, right? Whenever we plugged in -1, hey, that's just a reciprocal. Okay. Why do I point that out here? Well, guess what? Quotient rule. What operation are we going to use now? Quotient property, sorry. We still have x and y, it's just division instead of multiplication, right? So we're going to do the same thing we did here, but instead of addition, we need to use subtraction. Now, where is the negative at? Which term is the negative in front of? The subtraction part. The y, right? And we know that it should go there because where was the y to begin with? denominator. Is that clear to everyone? That's an important part though to see here, that similarity, that there's certain things that we can do here. If we wanted to, we could have wrote this as log base A of x y to the -1. And we could have explained it a different way. And we're going to bring that up in a second because as I deal with these properties, we got some other ones. So we go with the product and the quotient though, as far as the adding of logarithms and subtracting of them. Concerns there? All right. The next one I want to look at is the power rule. Okay. So if you had x to the m raised to the n, what do we do with those exponents? Multiply them together, right? So m times n. Okay. What you're going to find is the power property of logarithms is going to be very similar. Okay. But make sure you see again, it's all about the argument. It's a single logarithm, and inside the argument is x to some exponent. This is going to be where we see the power property come in for logarithms. What we're going to do is change that to n times the log base a of x. All right, I take that exponent and I brought it to the front to set up a coefficient of the logarithm. Where does this come from? Well, that's where I have an example here, right? The power property comes from the quotient, the power property comes from the product property, right? So remember here, you can rewrite x cubed as x times x times x, right? Well, since that's all multiplication, I can break that apart using addition. So the natural log of x plus the natural log of x plus the natural log of x. This would be a pain to have to do all the time, by the way, right? I can give you an exponent of 11. We don't want to do this. But what's going on with all of these terms? They're all natural log of x, right? Those would be like terms, right? The natural log, and they all have the same exact argument. How many of these do we have? 3, right? So guess what? 1 plus 1 plus 1 is 3. The power property keeps us from having to do all this work, though. That's why we like this. We don't have to go through all this just to say that. Okay, but I feel that's a good example to show how the power property works. Okay, the same thing can be set up here, right? Because if you had, say, x to the 5th squared, well, isn't that x to the 5th times x to the 5th? That's what a square means, right? Well, 5 plus 5 is 10. You could have just multiplied 2 and 5 to start. Okay, so same kind of idea there. Questions or concerns here with the power property? All right. Now, this list over here is just looking at the inverse properties. This is something that we have worked on as far as dealing with different things. That this is completely wrong. Give me a sec. Don't know what happened here. All right, when you deal with inverse properties, we've dealt with stuff like this throughout the semester, but now we need to set it in place for exponentials and logarithms. So the first one here is like, hey, if I see the cube root of x cubed, that's just x, right? If we see 5 times 1/5, that's just 1, right? These are some things that help us out dealing with stuff. What does log base 7 of 7 cubed equal? Now, a couple things you could do here. You could put the 3 in the front, right? But what's log base 7 of 7? It's 1, right? And 3 times 1 is 3, right? So if the base of the logarithm matches the base of the exponential part of the argument, all I need is the exponent, right? Hey, 7 cubed is what gives us 7 cubed. The same thing is true even if I put it in an exponential form, right? What is the base of a natural log? E. So if you have E raised to a natural log, right, that's going to give us whatever the argument was. And it doesn't have to be E. That's what the last one is saying here, that it can be any base, right? So as long as these bases are matching, in this case, just take the argument. Okay. The idea behind that, though, is the log is asking us what exponent will give us the argument, right? Well, if you take that value and raise it to that particular exponent, you're going to get the argument, right? So that's where that comes from. But make sure you see here, I did it with the log being on the outside and then the exponential part on the outside. It goes for both of them, right? Doesn't matter which direction we go there. Any questions, concerns? Now, this is going to help us out a lot. Okay, so here's one example where we can use it to our advantage. All right, so let's go back to our compound interest problems. This one, I said we're going to have an account that's used to invest money at 6% per year. Okay. I'm curious though, if it compounds continuously, how long does it take an investment to double? All right. What's some key things you're highlighting as you're writing this down? 6%, right? Make sure we have R equals 6%. Good. What's something else? Compounds continuously, right? The per year should be, I don't have to put that, right? Per year is kind of part of the context already, okay? Now be careful here though, the big difference is that 6% per year, but then it says compound continuously, right? The continuously is the key word there. What formula do we want to use when we see the word compound continuously? Anybody have that written down still? The amounts equals the principal times what? This is the E to the RT, right? The 1 plus R over N is the compounded in times per year, okay? The PE to the RT is continuously. Does everyone follow that? Now, did I give you enough information? The answer is yes, but it doesn't seem like it, right? Because what did I not give us that probably would have been helpful? I didn't give you how much is being invested, right? But what did I tell you we're interested in? How long it takes it for to do what? To double, right? Now, what does it mean to double? Mathematically, if it doubles, we did what? Multiply by 2, right? So understand that what you could do with that is just say, hey, A equals 2 times whatever I start with. Okay. A equals 2 times whatever I start with. So let's just plug in what we have and see what happens, right? So if I do that, this would be 2P equal to P, because we didn't know what the initial amount was. Not equal to, sorry. And then E to the 0.06 T, right? Right now, though, I said how long, so we're trying to solve for T, okay? What can I do to the P value here to get it out of the way? We can divide both sides by P, right? And I don't even have to deal with that anymore. So this will give us 2 equal to E to 0.06 T. Now, the nice thing here is how many variables are left? So coming from here, what's the only variable that's left? T, right? T stands for time, so wouldn't that help me for the how long it takes? Now, the problem is before we would be stuck here, right? What in the world do I do? But this is where our properties come in and help us, okay? What we find here is if I can introduce one of those inverse properties in particular, I can get rid of E. Well, what logarithm goes with E again? ln, right? So what we do is say, hey, let's take the natural log of both sides of this equation. So we're going to write it as the natural log of 2 equal to the natural log of E to the 0.06 T. Whatever I do to one side of an equation, I do to the other, right? So I'm going to take the natural log of both sides. Now, the natural log of 2, understand, we're just stuck with that, okay? But this is where our properties become very, very much helpful, right? What we just found is, hey, I can get rid of that E now. I don't need that because the natural log of this is going to give me that exponent, right? So on the other side, I'm left with 0.06 T. Now, you could have just wrote it as the inverse too, like we did on those first 2 problems. Please understand that. As long as you remember base E for the natural log, you could have just taken the steps we did on the first 2 I said to rewrite, could have done that here. I just want to make sure to show you how introducing the logarithm, like we've done other things, can help us solve. Now just make sure you see here then, dividing by the 0.06. will give us what we're looking for. We just have to go plug this into the calculator, and let's just round to the second decimal place. All right, just make sure again, you see here though it is in years, but it takes 11 and a half years for this to double at 6%. Okay. It's definitely something that you would want to look at too, right? How many of you already have investment accounts? Right? How many of you want to have an investment account as you start working? Right? This would be something that we could take this right now and apply it to life. In fact, have any of you heard of, well, what's it called? I was about to say Avocare, not Avocare. Primerica. You heard Primerica? Anybody interested in selling insurance or have sold insurance before? No? Okay. And that's one of the things they do in the area. My wife and I did it, but they had a formula that was kind of built off this idea here, right? Theirs was actually a little bit slower than the direct path, but I understood because there might have been some stuff I didn't know about, I hadn't learned about yet. Okay. But the key is understand when you start dealing with stuff that has interest involved, whether it's interest that's like, hey, I'm earning money on an account, or interest in, you know, say you have a student loan. How many of y'all have student loans in here already? That's awesome. I had a student loan in community college, so that's awesome. My problem was in community college, guess what I used? Not a student loan, but a credit card. Please don't do that. Please don't do that. Okay. Do not use credit cards to pay for school. Huh? No. You did that already? Okay. Did anybody use a credit card to pay for school? Please fix it if you did. If you did, please fix it as quick as, because the problem is what's the interest rate on the credit card typically like? Like 20+%. Let's just check it. Someone doing their calculator real quick. What's the natural log of 2 divided by 0.24? Let's just pick 24%. How many years? What'd you get?
I don't know if I typed it over. I got 2.9.
2.9?
Yeah.
How long does that mean it takes for it to double?
3.
No, just about 3 years.
Yeah.
Student loans typically, I think, are like 3%, 4%, right? So keep in mind, it's slower than this, which is better, right? But just keep those things in mind as you deal with it. Why is this practical? First thing, math side, hey, I just wanted to show the inverse property and how it's helpful, okay? But also take this practically, right? As you take this class, this is one area where you're like, okay, what does this have to do with me in anything? This affects our life every day. Sadly, interest is on everything. If you want to buy a home, if you want to buy a car, if you want to get student, if you have to get student loans, all this stuff affects us every single day. You can't get away from it. Even when you use a bank, how many of you use the bank locally here? Guess what they're doing with your money? Trying to make money off of it, right? Whether it's given to someone in a loan or going and invest it on the market, right? This is all a part of that, okay? So keep that in mind. With that said, though, to come back to the math, are we okay with why I picked A equals PE to the RT? All right. We're okay with this fact here that, hey, just because we didn't know it, we knew we were doubling at least. Okay. The nice thing here, like we showed, that you can just divide out whatever the initial amount is. The 2 is the key. Like, hey, I wanted to see how long it takes to double, so I got 2. If I said triple, we would expect to see 3. Okay. From here, though, what you find is that natural log of 2 and that rate really was the focus of this. Okay. Any questions though before we move forward to some other examples of using properties? The inverse property is definitely the focus of this though. Okay. Now, make sure if you need to, this would be the one I would say take a picture of or copy down, just kind of summarizes it. Make sure you see here, we went through the product, the quotient, the power, and the inverse property. There's a few others out there that we've talked about. So they could be like, hey, what's log base A of 1, right? Well, that's 0. Okay. Log base A of A is 1. I didn't put them here because we did those problems already at the beginning of the class. That's the only difference. Is there any questions where this stuff is coming from or what it means? All right. So One way to practice this is taking logarithmic expressions and either expanding them or condensing them using the properties. Okay, now I simplified the instructions to just expand the logarithm or condense the logarithm right now, but understand it's going to say, hey, use properties of logarithms to do something. Okay. What I want you to see here is these first three are all a single logarithm. They have a lot going on now, right? The arguments have a lot going on, but it's one logarithm. So what we want to do is use the properties to expand it or make it multiple terms that each have logarithms on them. Okay. So what does someone see going on here with this argument that we can focus on? There's an x squared, right? So we might need to deal with that at some point, right? What operation holds the 125 there with that x squared? So if I wrote it out, it'd be 125 what x squared times, right? So there's multiplication here too. What you're going to find here is you need to deal with the product property first. Okay. So what you want to do is say, hey, I'm going to break this up as log base 5 of 125 and log base 5 of x squared. We're separating those factors. What do I need to put between them though? What do I put here? A plus, right? Because it's multiplication, right? We're going to make it separate terms that are positive. Okay. Here's where we have to deal with the exponents though, right? So as you said, make sure you see that 2 I can deal with. Right? That's where you want to deal with the 2. Once the x squared is the only thing there. What's going on with the 125 though that I have to be careful with sometimes? Does 5 divide into it? How many times? Well, yeah, it's 5 to the third power, right? So understand that if you do the division, right, 5 goes into it 25 times, and 25 is 5 times 5, right? So we could rewrite this as 5 cubed. Well, that would make both these bases exactly the same, right? So what we find is, hey, this one I can evaluate it just down to 3. Not going to happen all the time, like I said, but here's one that I could actually just get what it is. That sounded painful. All right. Are we okay with why we have a plus sign now? Any concerns with what happened to the 5 and the 125? Now, this is considered expanded because of the fact that we have multiple terms rather than just one term. Okay, sometimes you're going to be able to evaluate, sometimes you won't. I will say this on the final exam, there's sometimes going to be problems that can get a little bit more involved. I will make sure to clarify as I see it, kind of what my expectations are. Okay, 125 here is a power of 5. Does everyone see that? But if I put 75 there, it gets messy. How many times does 5 go into 75? What is it, 15 times? The problem there is what's the factors of 15? 3 and 5, that's not all 5s, right? So there's ways we could discuss breaking it down, but I'd rather just take just direct ones. Is that clear to everyone? So something like this where, hey, it's only 5s, that's my focus. The 1296 we did, right? It was just 6s. That was better. Okay, so keep that in mind. I'll make sure to explain that as we get closer to the final. With that said, remember, as we go through this, we'll have class Monday and Tuesday next week, Thanksgiving break, and then the next week I have a couple things and we're going to review for the final as well. One thing I do want to make sure to point out, I will not be here tomorrow. Okay, I'll come up here for my office hours, so if you still need help with something before class time, I'll be here, but we have an appointment event thing going on that I found out last minute that I need to be at. Okay, tomorrow I will not be here. Is that clear to everyone? All right. All right, moving on to the second one now. What's one thing that I put differently on the second one that I had to be careful of? I got a square root involved we're gonna have to deal with, right? But I also got division, right? So what I think we could deal with, let's deal with that division first. So we're gonna put log base 3, and we're gonna do the square root first, minus log base 3 of the 9y. Now, I also did something different with the square root because this is where we have to remember that radicals can be written as exponents. Okay. For the square root, remember, we can write it as what fraction? What's the known value for a square root when we look at the, it's 2, right? So understand though, we don't write it as 2, we write it as 1 over 2, right? So this is where we're going to be like, hey, this is our power. And the denominator is our root. Okay, so just make sure you remember that. We're going to need this here because that's going to allow me to treat that 1/2 like we did the 2 up here. Okay, now what do we have to be careful with this one though? It's 9 times y, right? I'm not done separating that then. I could still break up that multiplication. So make sure you see here that as we deal with this, the first one we can bring out the 1/2. Now make sure you keep your parentheses on the x minus 1, okay? But over here, what we need to do is make this log base 3 of 9 minus log base 3, not minus, sorry, plus log base 3 of y. Right. It doesn't matter. I started a bracket, so I should keep it brackets. The key being there is I separated the 9 and the y using the product property. Okay. Now, what does log base 3 of 9 equal? It's 2. 3 times 3 is 9, right? So there's 2 3s. Make sure you see that that's 2. But what you're also going to find here is we need to distribute the negatives to both of those. Okay. So our final thing that we can write here would be the 1/2 log base 3 of x minus 1 minus the 2 minus the log base 3 of y. Now, does it make sense that this is negative and this is negative? Why would you say that? All right. But where were they both at in the beginning that would say they should be both negative? Weren't they both at the bottom of the fraction, y'all? So technically speaking, you could have separated like this from the beginning, just remembering, hey, both of those need to be subtraction because they both are in the denominator. Okay, so you could have skipped this step altogether if you wanted. As you practice this, I'm fine with you condensing the steps. Is that clear to everyone? That's one thing I want you to see. As you practice this and you get more confident with the properties here, you don't necessarily have to break it down one step at a time. But if this helps you to write it this way before going here, do it, right? Do what you're comfortable with. What you're going to find is, though, you could probably look at a problem like we see here and say, hey, these 3 things are all separate factors. And what do all 3 of those things have on them? They all have exponents, right? So guess what? I could put each of those exponents to the front. So I'll have 3 natural log of x plus 7 natural log of y plus 2 times the natural log of x minus 4. I made not 1 natural log, but 3 of them, right? Because I had 3 things being multiplied together. So I have x by itself, y by itself, and I made sure to keep parentheses around x minus 4. Where did all their exponents go? Where did the 3, the 7, and the 2 go to? Yeah, it just became a coefficient, right? So they're there. We just remember, hey, power property, I can move that to the front. Okay. Now here I'm telling you by directions to do this, right? So keep that in mind. For this particular problem, I'm telling you to do this. All right. The next problems, I'm going to tell you, hey, I got multiple terms. Let's condense them. Okay. One thing you're going to find, though, as you deal with this, the situation will often determine what we need to do. The situation will often determine what we need to do. Okay. So here we started with a single logarithm and we expanded it to multiple terms. The number of terms we get kind of depends on what we're able to do. Here, I'm going to give us multiple terms, and let's write it as one single logarithm. Okay. So as you copy down the first one though, what's something that should stand out to us?
The one.
The 1/2 is going to be something we deal with, yeah. What's going on with each of the logarithms though that we need to see? They're all base 7, right? That's an important part there. In order to deal with this, they all had to be the same base. Okay, so that's definitely an important aspect. Now, what we want to do though is kind of take each step at a time and start breaking this down, right? Well, not really much I need to do with this, but what can I do to help start condensing this one? What's in front of my logarithm that I'm able to move?
The 3.
The 3, right? Where can I put it at using my properties? All right, so I could say, hey, this is log base 7 of 5 plus log base 7 of x cubed, right? What did we just say 1/2 was though?
It's a square root.
That's, hey, you could just go straight to square root when you see that. That's going to be up to you to remember that, right? If you put it as an exponent, it's not technically wrong, but also make sure we're comfortable like, hey, the 1/2 is a square root, 1/3 is a cube root, and so on. Okay. With that said, though, all of these things are positive, right? So my next step is to put it as a single logarithm where I'm just multiplying all these things together. So 5x cubed square root of x minus 2. I'm putting the parentheses there just to ensure that, hey, this is one logarithm. These are all inside the argument. Watch out for subtraction, right? Subtraction means it needs to be in the denominator. That would be the only thing I can add here, right? Something with subtraction. Questions with that one? What do you notice about the next one?
It was the same except for
Okay, so not exactly the same, right? I can't just add them together. It'd be nice if you have like terms, right? Just add them together. They're both the same. Just remember, hey, 1 + 1 is 2. But because one's x minus 3 and one's x plus 3, I have to go to my properties, right? What operation am I going to use to combine these two factors though? So I have x minus 3 and x plus 3. What operation do I need to have between them? Multiplication, right? So do I really need to put anything then? Just make sure to put them right next to each other, right? So let me scoot this on over and bam, there's my logarithm. Okay. Now, if you wanted to, you definitely can multiply this out. I will say this, if it doesn't tell you to do that, don't worry about it. Okay, is that clear to everyone? Doesn't directly tell you to do it, don't worry about it. Questions or concerns there? Do it feel okay from the condensing perspective then? You need to put, if you need to put the brackets here. Okay, and I would definitely say you want the, it doesn't have to be brackets now. I'm just using brackets to highlight the fact that we had parentheses there, okay? So I was just separating it. But you definitely need it here because of that subtraction, right? So we need to show that, hey, all of this is inside. Up here, I would still encourage you to put it to make sure to show, hey, this is all my argument, okay? Now, what I want to make sure to show as we do this is that we're not going to just have this for the sake of condensing and expanding, right? We might need this for different purposes, okay? One thing that we can be stuck with is, like, say we're trying to solve this equation. Okay. This is where properties are going to become very important for us. All right. Now, as far as equations, 1-to-1 is a great aspect, right? We're gonna make sure to bring that up as we move forward, and we're gonna practice properties and this stuff as well as we go forward. But this is one example to me that highlights why would properties help me, okay? So what do we notice about the logarithms that we have here? Or what do you notice about the logarithms? Same base, right? Because of that, I can condense this. Because they have the same basis, like, let me condense this. The key is to recognize, hey, since they're being added together, I'm just gonna multiply them together now, okay? So I'm gonna take this and say, hey, I can get to a single logarithm, log base 2, x times x minus 2. Now, the reason I like this is I only have one logarithm now. And the only thing on the other side of this equal sign is a 3. Right? So using an inverse statement, right, I can get this to look like x times x minus 2 equal to 2 to the third power. Right? Going from a log base 2 to an exponential with a base 2. Well, what type of equation is it at that point? No longer logarithm, right? Now I'm solving a quadratic. All right. So remind yourself of quadratics. Hey, the first thing I need is equal to 0. 2 times 4 is 8, right? So this one is factorable. As long as we use -4 and +2. And I get 2 solutions. Okay. So using this idea of condensing this to a single logarithm allowed me to just do a direct inverse to solve. Now, things that you have to be careful of, right? What numbers are not allowed in here? No zeros, no negatives, right? So technically we should make a note of that, like, hey, x better be greater than 0, x better be greater than 2. And really, that's all we care about is x better be bigger than 2. Okay, we got to go with the one that's more strict. With that said, can I use both of these then? Kind of just highlighting what we've talked. Right, so we need to cross out the -2, and then understand that at that point is what we call those extraneous solutions. We didn't do anything wrong, it just happened to come up, right? So remember, just cross it out. Don't worry about it. We don't need it. So the only solution that we would get from here is the 4. But the only reason that we're able to do that is through the use of our properties. And if I use addition, guess what? We could also use subtraction. Now, please keep in mind, as we get into the equations, we're going to talk about some other stuff, like we might have to move stuff around sometimes. My focus right now is the properties, okay? So as you do this, make sure you're highlighting the fact that the logarithms I choose both have log base 3. That's an important part of this. If they're not the same, we're limited on what we can do, but because they are the same, we can deal with this, okay? Once I get here, make sure you see the big difference with this one though, because I'm using subtraction, right? So when I bring this together, I would have to write this as log base 3 of x plus 2 all over x minus 5. Okay. So now I'm using a fraction. Whatever's behind the subtraction, that's what goes in the denominator, right? Negative exponents is where that comes from, right? So negative exponent, hey, that's going to be in the denominator. Okay. With that in place, though, what do I need to move now? I need to deal with the 2, right? But remember, this is where, like, hey, with logarithms, I can change it to an exponential to allow me to solve, right? And this is where that idea of an inverse comes in. Instead of log base 3, hey, I have 3 squared now, okay? Now, make sure you remember here, though, as far as dealing with these, whenever you have a rational, we want to eliminate the fraction with multiplication. So by multiplying both sides by what's in your denominator, that just goes to 1, so I don't need it over there, okay? And then I'll have x plus 2 equal to whatever I get over here. This time it's just linear, so I'm going to run through it real quick. Not the nicest looking answer, right? Didn't need to look nice. But the one thing that you always want to make sure to do is anytime you're dealing with this is don't forget the fact that, hey, we have things in place that have to be true. Specifically greater than -2 and greater than 5, which means our focus is the bigger of the two, right? The 5. Well, what's 47 divided by 8? Something in our calculator. That's all you need to double check real quick. 47 divided by 8. And then hit that S to D button so you get a decimal. All right. And the key is what decimal do we get? All right. We get 5.875, right? Is that bigger than 5? Yeah. So we're good to go. Okay. That would be a tough situation here. Just make sure to check your fraction to see if it's bigger than 5. Now, again, my focus here is everyone okay with me going from here to here? Is there any concerns with using the quotient property here? All right. Now, this is us using the inverse idea, right? Rewriting using inverses. So technically, we could have used the inverse property, but what you find is you can write this out like this, as I have here, but I would completely accept it if you went from here straight to here. Just writing it as an inverse. Is everyone clear on that? So whether you use the property here or not, it's okay. Okay, textbooks are going to be different on there, right? Sometimes you'll see an author actually write out, hey, I use the inverse here, right? Sometimes they just switch it and you got to be like, oh yeah, that's because of the inverse property. Okay. Now from here, this is just me reviewing how to solve the rational because we haven't really done that in a while. Okay. Even with the inequalities, I kind of took some other methods into consideration. Okay. Any questions though with the properties that I can help someone feel more confident with? All right. So as I mentioned, like as far as dealing with properties, we definitely want to get comfortable with, where'd it go? Sorry. This is definitely something we want to be comfortable with here as I showed her, right? Make sure we're familiar with this. The good news, it's not made up, right? There's still connections to our rules of exponents. They are different though, so you definitely want to make sure to practice to remember some of those subtle differences. Make sure you can use those properties to do what you're asked as far as direction. So remember here, it was a single logarithm. We want to expand it as much as we can. What we're looking for is, I can't do anything with x, so I just left it by itself. We can't do with anything with x minus 1, so we just left it in parentheses, right? How far can we get before we're not able to do anything? Okay. The condensing, use the properties to take multiple logarithms to write it as a single logarithm. On the condensing problems, you should only have one logarithm left. Okay. These problems are designed to practice those properties. That's the key behind it. This is where we're going to see some of it come up, though, is dealing with equations, right? So the purpose of these two equations was just to show that, hey, once I do the condensing, it allows me to solve. Okay. Once I do the condensing, it allows me to solve. Just know that as you saw here, be prepared for anything. Polynomial, linear, be prepared for any type of equation after that. Rational is the part I was supposed to be saying. Okay, so keep that in mind. Any questions or concerns though, before we finish up today? Now, what did I say about tomorrow?
You're not moving to